Okay. All right. So, just taking advantage of who's actually here. Jane, tell us a little bit about CPU offloading and like what the problem is, and what's happened.
Yeah, sounds good. So I think some of us, like Mark in the room and others, have heard of have realized that memory efficiency is like a big problem or a big ask today in the open source. I mean, everywhere really, but specifically in the open source community where they don't have that many GPUs. And one of the methods to like save memory is to be like, hey, I have this much VRAM, but I have a ton of actual CPU RAM. So the big like motivation behind CPU offloading is, hey, only put things into GPU when you're computing. So once you're done with computation, move that tensor, move whatever memory back onto CPU. And that motivated, I guess, Les, who's not here, to write like a page optimizer, which is like writing a specific kernel to use unified memory. But then I was talking to Ed and Albin and Christian and being like, okay, so unified memory kind of sketchy. Can we do this in a much more like safe way that we can control and figure out memory? And the way we did that was we wrote this offload tensor using torch dispatch that would check before every op to be like, do we have enough memory? Do we need to move any memory off? Can we pull in all the tensors necessary for this op? And basically do CPU offloading per op in that way. So that is one potential API. Okay, I'm gonna pause here to see if people have like thoughts already. Or Ed, if you have questions, but I have more to say.
Keep going.
Okay. So I was thinking about this, Ed, and I was like, this sounds like a great thing. I could tune this heuristic really well. However, if I'm comparing the offload tensor, which uses torch dispatch, to something like page optimizer, if I'm just like an open source user and I'm like, which one will save me more memory and which one is more like fast, it's gonna be page optimizer because that's like inside the kernel. Every time it needs some sort of memory, it's already in unified memory, so it will do that paging kind of like on the fly. Whereas for the torch dispatch mode, where you're basically interfacing before and after every op, you don't get as much granularity. So in my head, I was like, I feel like there are uses where this offload tensor is nice for just like a lightweight 100 line program anyone can put into their thing. But for like true performance, like cutting edge work, I think we're gonna need an API that goes lower and that does like work with CUDA caching allocator, probably like handle streaming, like all of those things to actually hide the communication and computation.
Okay. Any
But I haven't
questions?
actually done one. Oh yeah.
Any questions for Jane? I have a poll in the room. Is anyone here working in like memory constrained environments? Have any thoughts in this space? Maybe looking at the quantization people. Okay. Well, we won't belabor it. Thanks for giving us the update, Jane.
Yeah, thanks,
So
Ed.
I have a
yeah, go
quick
ahead.
follow-up, Ed, on that topic. Sanket, who's working on the distributed team, is looking into tracking memory. So we have a PR with a memory tracker that works under fake mode. If you want to guess how much memory is that model going to use without actually running any computation or actually using any CUDA memory, but still knowing how much is going to be used. If you're interested in that topic, ping me. We have a bit of work there.
Okay, I actually have one question, which is so you basically concluded that we probably do want something lower level, but so what exactly is the plan? So is the plan just Les Wright keeps doing stuff with UVM, or is there actually going to be an infra project like at the C++ level?
Oh, at this point, I think I'm not sure if we've like ascertained it's worth doing yet. Like, it's still a needs research stage of our triage thing of like, hey, if less like is Les's thing proven out yet? Not quite sure. Like, we'll see how that goes. And if it's compelling enough to move into core, then we should really consider, okay, how do we offer something like this, but from a core, like as a core offering that is safe and composable.
Okay, because like in general, our stance towards UVM has been, well, you can turn it on if you want, but it has some pretty weird performance characteristics. So you're kind of on your own. You got to figure it out when you do this.
Yeah. Yeah, so I think if let's say like page optimizer becomes a big hit, then I think the thing I'm thinking of is can we do this in a planned way where we can like offload like instead of dynamically offload and trusting unified memory, it's kind of like do a thing that FSDP does, which is like you know you can only fit 1/4 of your tensors or something at a time. So stream it that way and be very static about how we prefetch and offload. So that's the type of API I think I would lean towards in the end.
Okay. Let's move on. So I
Real-
wanted.
One,
Oh, go ahead,
one,
Elias.
one last quick question on that. Comment on that. I know in the like Apple, I forget what their framework was called, but they like have one of their big selling points is unified virtual memory. Um, they can, I don't know, just as a like it'd be nice to have some for Mac. I guess they claim it provides a nice user experience with like the M1 processor, and I wonder like I don't know if there's we haven't really focused on Apple too much, but like that is one of their competitive advantages they claim relative to PyTorch.
Alvin.
So the nice thing there is the GPU memory and the CPU memory are physically the same thing. So you don't need unified memory because they are, you can actually hog off all the memory thinking using GPU at one go. The only performance that you leave on the table is when you transfer something from CPU to MPS. It could be a no-op because it's literally in the same memory space that both can use. And today we do an explicit copy. So that is one thing that we could look into. But in practice, copy from CPU to GPU is not that problematic when you are already in that world where your GPU can access all your CPU memory at full speed. And so you just put everything on the GPU all the time, and you just never have a CPU buffer to begin with.
Do you mean like that if you've got like if you've got PyTorch code that says CPU and then says whatever, yes, and you transfer it, that we will do a transfer?
Today, yes.
Yeah.
Okay. We could make that a view op, but cross-device view ops is not a thing we have. We could add that concept. We have cross dtype view ops already. We just never had the need for it yet. But yeah, if you have a use case where you care about that and make that fast in a view up, we definitely can. We just need to implement it.
Okay, let's move on. So I don't see a Christian Persh here still, so I'm gonna kick that some more. So Vincent Moens actually isn't here. He has a topic for 2 weeks from now, but he's not here this meeting. Richard, is there anything you want to give us an update about regarding TorchDim?
Not really. We're at the same stage we were before, which is we're not sure how to proceed. There are two options for actually productionizing TorchDim. The first is we rewrite TorchDim using Torch function subclasses. And the second option is we just keep going with Zach's prototype and we just keep on hardening it.
Is there anything this meeting can help move this decision along?
I'm not sure. I think we just need I've mostly been pushing us towards the torch function approach because it seems more morally correct. I think what we just need to do is sit down and prototype it out and then see what breaks and then come back here.
Okay, thanks for the update. There was actually some discussion about from Horace about how well we support torch function mode in Dynamo in Workshop, and I think the answer was we have some of it, but not all of it, and needs some focused attention. Okay, let's do another topic. So, Brian, do we have Sam here? Tell us about Tell us about AOT Autograd caching. What's new?
Yeah, I don't know if Sam's here. So I should probably talk to Sam some more about just like ordering and who's working on what. But I guess the short answer is nothing, no work has happened for AOT Autograd caching so far. But do you want me to give any of the background on like worm start stuff or just like potential ideas for where to go for AOT Autograd caching?
Give us briefly, you know, what we're doing and then what the current state is. I am more interested in the current state.
Yeah, I guess the brief problem statement that Horace and other people have already mentioned is basically warm starts are a thing we want to make better, where you've compiled a thing before, you want it to be fast when you run compile again in a new process. And there's caching at a bunch of levels, and today there's caching at like the inductor level in a few places, and there's not caching at the AOT autograd level. And so what that means is that every time you run torch.compile, Dynamo does a bunch of work to trace bytecode and get a graph of torch IR, and then it always hands that graph to AOT Autograd. And AOT Autograd does a bunch of expensive compilation stuff to trace the torch graph from Dynamo into a graph of functional A10 ops, and generate this like runtime wrapper that sort of wraps the generated inductor artifact that does a bunch of things to kind of handle autograd edge cases. And so right now, one thing you can imagine doing is taking that runtime artifact and making it serializable so we can put it on disk, and then having some kind of cache where we can cache like the torch graph from Dynamo and all of the relevant metadata. And then that would be the cache key. And then the value is this like serialized version of the AOT Autograd runtime wrapper that lives on disk somewhere. And I think a few people have discussed like a few ways of trying to do this. So one like very cheap way that I proposed is the like, what is this runtime wrapper? It's basically like a bunch of Python glue that calls a custom autograd function that calls some inductor artifact. And that's basically all Python. And so you can imagine using like pickle or something to just like serialize the Python to disk. And maybe that's a good like first step prototypey thing just to like try out caching. Another thing you can imagine doing is that you could take the runtime artifact and trace it into an FX graph. And again, like the runtime artifact is effectively just like a bunch of Python conditionals detecting if we need to do things for like aliasing a mutation, and then a call to an autograd function. And so if we can, one thing we could do is like represent the autograd function as a higher order op like we do today in Dynamo, and represent the inductor artifact as some kind of custom op, and then trace through all of this like Python conditional goop in AOT Autograd, and then get out an FX graph. And in theory, if we can trace that as a pre-dispatch graph and serialize it, then we could also dump that to disk. So I guess those are the two like high level ideas, one easy, one a little harder, but any like high level questions about that? Yeah, Oz.
So not exactly a question, but perhaps like a follow-up is, once we are able to, now that I have been looking at like this like remote caching stuff, once we are able to serialize both inductor and also autograd, we should be able to just like upload all of this to remote cache and be able to like just skip pretty much all of PT2 compilation. I think that might be a nice like a cherry on top for the internal workloads.
Yeah, I think that makes sense. One question I have is I know we have like multiple levels of caches today, like the Triton cache and the inductor cache. And do those all have some unified like global memcache thing that's shared, or do we have like different and I don't know, general caching logic for that?
So right now, like all of these caches use the same caching backend, but they all have their own keys because we wanted to make them independent. And we can also like use this same caching mechanism for like inductor and autograd and get like the same benefits. And like if we were to do this, like assuming this works perfectly, like only Dynamo would need to get run. And since Dynamo is only like 5 to 10% of compilation, this should shave off like a lot of the compilation time for all internal workloads.
Yeah,
One
so
question
that
I
makes
have
sense.
is so ostensibly when I do AOT autograd caching, I will need to save the inductor products to the cache as well, because it's everything underneath plus some extra stuff. Are we expecting to deduplicate these, or are we just gonna have another copy of everything in the OT Autograd cache?
I think that's a good question. I don't think the design is baked out enough that we have an answer to that yet. I could imagine doing either of those things.
Okay.
If you're just storing them on disk, does it matter?
No, I'm talking about the cloud cache situation, especially.
Oh, sorry. Okay, I didn't catch that. I don't think we can deduplicate them, but it probably doesn't matter at all, because after all, we're storing very little information, so we are not even using that much memory. But perhaps with the AOT Autograd, there might be more to cache. In that case, we can do some deduplication, but I really don't think it's going to be a big deal.
All right, thanks for the update. Do we have a Christian here? No.
I pinged him and he did not see my message.
Okay. So let's see. All right, I wanna give an update about int float intermediates to Dynamo representing graphs. I don't have a doc. Actually, I do have a doc. Let me share it, I guess. Okay, so there are a number of different things that we're trying to solve for with this line of work. So to just briefly discuss some of them. So one is that let's say that you have an integer or a float, like a plain Python int or float input to a torch compile block. We sort of support it if the integer is dynamic. We definitely don't support it if the float is dynamic. This is kind of a pain for optimizers and people writing custom operators and a variety of other miscellaneous situations. So it would be nice if we can actually make these dynamic when they vary without having to recompile everything when this happens. A second thing is we have some softness in our size computation when floating point operations are involved. So a common situation here is something like I am doing some very fuzzy upsampling, downsampling type thing that involves dividing and then maybe taking square roots or something like that, and then taking the floor of the result to get my actual size. So this is kind of been kind of creaky in the past. There are a bunch of cases where this causes problems when you go into float when you do size compute. Another thing is from the perspective of inductor and also from edge, when we are producing graphs, we normally have graphs that have a lot of tensor compute. And because of the introduction of symbolic sizes, dynamic shapes, you can also have integer compute in the graph. And if you follow the same line of reasoning for floats, you can also have float compute on the graph. So you end up with a situation where if you're a backend, you need to not only be able to deal with aten.sign, but you also have to deal with math.sign because they're different things and they're different types. And that's also kind of a pain for the backends. So what are we doing today and where are we headed? So today what we are doing is we have this thing called Cement, and when you do dynamic operations on plain Python ints, they turn into special integer only operations which are tracked via the symbolic shape system. These can go into floating point operations and go back out, but it's kind of buggy. Float dynamic inputs don't really work at all. And we have the invariant that you can only pass in integer inputs to inductor compiled graphs. So no floating point inputs. Where are we going? So I've been trying to figure out what we should do to make this all better, and it's just kind of difficult. So one thing that I was thinking about and I pitched at the Dynamo sync earlier, or PyTorch 2 sync, was maybe we should have a guard graph where when we have operations on floating point operations, we don't put them actually into the shape environment because maybe they're not actually size-like computations. We're just going to trace them into a fully functional FX graph, which represents, a bunch of compute before it actually goes into size computation. So that's one of the ideas I've been playing around with. But the other thing that I've been working on is just sort of making what we are doing today better. And so there were two parts for this. So part one is when we have floating point computation, like let's say you do a square root inside of size computation. What we did previously was we sent it to simpy.square root. And simpy.square root actually is its own thing. It is represented by the real number semantics. So if you do something like square something and then square root it, simpy will simplify it into a no-op in this case, because squaring something then square rooting it is a identity operation. And so simpy semantics for square root are sort of like infinite precision, especially if you do it on an integer. But floating point semantics for square root are not like that, right? They are not infinite precision. There are rounding errors. So one of the changes that I've been playing around with is, what if we don't actually use any of the simpy built-ins to represent these sort of weird floating point functions? What if we just have an opaque unary custom simpy function, which doesn't have any, symbolic reasoning associated with it? All it is, it says, hey, well, when you give me a float, I'll do some opaque floating point computation and you'll get that out. And that's all you get. So I can constant prop, you give me a floating point input and nothing else. You never can eliminate me from the graph. And I did this for all of the weird math ops we support. We actually, for some reason, support sine and cosine and tan in symbolic shape. You're never going to use these to do size compute. They're just in here because when people took in integers as arguments and then did things on them, it just happened to get shunted to this subsystem. So if we do this, actually, it solves a bunch of bugs, and we can basically add as many operators as we want, even if we don't know how to symbolically reason about them, because they just get represented opaquely inside of the size graph. So that's kind of nice. That kind of helps with the problem where we used to have a bunch of bugs related to when you temporarily go into floating point and then go out. Like sometimes the result would not agree with eager mode because we had somehow done the computation in some other way. But it doesn't solve the other two problems, namely not wanting to have weird floating point operations in the graph, and what exactly are you going to do with float inputs that are dynamic. So I'm going to pause for a moment. Any questions about this? The idea being doing opaque unary functions inside simpy in symbolic shapes.
You mentioned that people want to do a square root and a round to an in and then treat that as a size. Do we still need some analysis thing to know that the output of all of that is a size integer?
Yeah, so that's a great question. So I said we don't do any analysis, but that's not strictly true. So there are two things that we do. So one is that we still propagate hints. So if you knew that the input was 64 and then you square root it, the result of it is 8.0, the hint. So if we do a guard on the result of the expression, we still know what the actual value is, and we can go ahead and evaluate the guard. This, by the way, was part of the reason for a lot of the softness in our intermediate floating point computation before, which is that we would evaluate the hints based on what simpy thought they should be, which was not the same thing as what regular floating point would do. And so we'd make conclusions like, oh, this is true, but actually it's false because, simpy didn't round, but real floating point rounded, and so the results were different. The other thing that I'm doing, but I'm not sure if this is okay or not, is we have this thing called value ranges analysis. So value ranges analysis says if I have some variable, sometimes I know that it's greater than or equal to 0 and less than or equal to some other number. So I can have a range of possible values. And then when I do operations on it, I can update those ranges, right? Like if I do a monotonic function, then I just run the function as well on the low and run it on the high. And there's various rules for various operations. So we actually have rules for most of the weird operators we also support, including square root. So I'm still sort of praying that these sorts of simplification rules are okay, even in the floating point case. I'm not really sure if this is true or not, but we're also still doing that right now. Did that answer the question?
That's it. Yeah. Thanks.
Okay, so this is like simple and not disruptive. Yes, NYC.
I don't know if I just missed if you mentioned this already, but why not just like, I think at one point we were talking about this for, I guess, the third thing in the hierarchy of needs for optimizer of just like, hey, just convert them to tensors. And here I think the approach is, oh no, fit everything into SymPy as much as possible. So what are the trade-offs of just like making them into scalar tensors and treating them like that in the
okay,
graph?
that's exactly what I wanted to talk about next. So this strategy doesn't require very much work, but it doesn't solve the other problems. And one of the problems is, what if we wanted to turn it into tensor compute? This is, I am not sure. I don't know how I want to do this. So the working plan that I've been turning around in my head is something like this. So okay, let me take a step back. So one of the reasons why deciding whether or not to make something tensor compute or not is difficult is because a constraint that I've placed, which, if you want to disagree with me on this, you can, but which is that size computation should not go into tensors. If I, have S0 and S1 and I cat them together, computing S0 plus S1, I don't think I should put S0 and S1 into a tensor, then run torch.add, and then .item out the result. Like, this just seems bad. Like, so it would be high overhead. In principle, the overhead could be reduced by, sort of clever application of compilation style techniques, but it just morally feels wrong to me to do it this way. So I want size compute to still happen without being tensorfied. Any
that
objections?
sounds fine.
Yeah. Okay. But given this constraint, I have another problem. And so my new problem is that, well, how do I tell if any given piece of computation is size compute or not? And the answer is, I don't know. Like, let's say that I have an integer argument to a function that I'm about to compile. Is it a size? Is it not? I actually have no idea ahead of time. What I have to do is kind of look at how it ends up getting used. And then if it actually gets fed into a tensor, constructor, then I'm like, aha, it's a size. But if instead I divide by it, like, pretty common to square root the numL and then, use it as a, normalization factor, well, it would have been okay to do tensor compute in this case. So the bad idea that I have, like the simplest possible idea I can think of to do in this case is like, well, put everything into some graph somehow that doesn't make a commitment as to whether or not it is size-like or not. And then once I have like found all the outputs which are size-like, do a dependency analysis. So everything those quantities depend on is size-like and should not be tensorified, and then I tensorify everything else. Seems kind of complicated. I don't know, but this is the best idea that I have right now. Opening the floor for questions or comments right now.
I mean, what about stuff that's used both ways?
If it's used by a size-like, then I don't want to do it in tensor.
Okay.
That's the answer. I know Jansel's here. I don't know if he's got any thoughts.
Is there a more specific question? I think I talked a bit about this with you in the past.
Yeah, we have talked about it. And I think your opinion is that, well, we can just do tensor compute, and then we have a way of turning tensor computation into indexing expressions via indirect indexing. So it's not a big deal to do the compute in tensor versus not. So I think I understand your position. I just don't like it.
Yeah, I mean, there's already a bunch of places where we're like wrapping scalar values in one element tensors and shoving them into inductor, and it's kind of annoying. It propagates to a bunch of headaches. So I think like the real acute problem is like what if we use this stuff in guards, and if we use it in guards, then that doesn't work because you can't, like, the sort of wrapping in tensors happens sort of inside the function, and the guards happen before the function. And so I think like I think I'm like more interested in solving sort of the like how do we guard on this problem, but and like in sort of the wrapping in one element tensors, like it's annoying. I don't like it, but I don't really have a better idea of how to do it. So I feel like wrapping it in one element tensors is fine, and I think there's reasons why we're gonna have to continue wrapping it in one element tensors.
So just to give a sort of counterfactual way, so the logical endpoint of my bad proposal is I do not immediately wrap floating point computations in one element tensors. When I do operations on them, I end up recording a bunch of floating point operations, whatever, into the SymPy expression, which has tons of random opaque, unary and binary and whatever functions for all the things we want to support. Eventually, I'm done, and if I've guarded on it, then I use that SymPy expression to generate a guard expression, which I can go ahead and guard on immediately. And any of this that doesn't get guarded on, doesn't get sent to tensors, I then turn it to tensor compute post facto. I could actually just retrace it with a tensor float instead of a float to get the tensor version. So this is my very bad, no good proposal. That is my best idea so far.
And to clarify, is this idea bad purely because it is way too complex for what you think it should be?
It's really complicated. Well, I'm just thinking about implementing it. I'm like, oh my god. There's so many parts.
Okay, another question. If you do the first proposal, which is just like shove everything into SymPy, as much into SymPy as possible, this means that the third point here is not solved, right? Like we still have like the missing, like there are still dynamic ints and floats that are not sizes related that then don't get handled in this way.
So there's also like the terrible like do nothing proposal, which is for integers, you always like we keep adding stuff to the SymPy language until like all dynamic int stuff can be computed, but it's always done as integer computation inside PyTorch, and then floats never get turned into integers, so they're always 1D tensors. We always decide they're 1D tensors, and we always just do propagation with them as 1D. So if you have something like a scale factor, which is float, and then you eventually put it into a size, this would end up doing the unbacked cement path, because what would happen is you would have been doing tensor compute on it, and then eventually you need to pass it to a factory function, so you need to call .item on it, and that gives you an unbacked cement in this case.
Wait, but that's only if it gets used in a size somehow.
Yeah, only if
so
it
in
gets
like
used in a size. Hey, Horace is here.
Okay. So for optimizers where it doesn't get used in a size because it's like a decay factor or something,
then
or
it
like
all
LR,
works
then
out.
it's
Yeah, that's right.
okay.
Okay, so that's everything I have right now. I'm gonna keep poking at it. I'm on vacation next week, so I'll like just be kind of thinking about it. But yeah, that's where I'm at right now. Okay, what else have we got on the list, or if there are any other questions? My workplace chat has disappeared. Okay. Vasily, you're here. Anything about MX dtype we should talk about?
Well, we're starting to figure out how to bring MX dtypes to PyTorch. A lot of details left to figure out, but we want to have a tensor subclass wrapper, which is going to contain the underlying scale and raw data elements. And looks like we have rough alignment that those underlying data elements are going to be Python dtypes eventually in core. some of those D types are sub-byte D types, like in NF4. So we'll have to kind of figure out how that works and battle test it. I don't have a doc or anything at this point, so I guess it's just a quick status update.
Any questions, comments from the room? I have a question. So one of the things that Greg has been asking about is essentially we can't really work on these D types until we actually know what the like hardware instructions are going to be in some sense. And so the question is, what work can we do ahead of time before we actually know these things, just to be like ready to go once the details hit the ground?
Yeah, so I guess maybe one piece of context here is there is a way to use these D types if you want to do your maximal node precision, which I think what you said definitely applies to that. And you can kind of guess based on crumbs NVIDIA gives us and what that's going to look like. But there's also another set of work which doesn't require any hardware support. And this is if you're like memory bound and you just want to use this as a storage format. So for that, we're not really blocked on anything.
Any other questions, comments? Okay. All right. Christian's not here, but I do want to talk about it. So let's talk about it. All right. Let's talk about NF4. So last time we talked about NF4. Essentially, the difference between MX and NS4 is NMX is getting hardware silicon support. So we're just gonna like do stuff in core as we need it. But NF4 is part of like a big explosion of everyone and their dog, wants to come up with, quantized D types, and they're really just used for storage. The actual compute involves sort of uncompressing them and then doing regular kernels on them. And so the big question is, what do we do about all of these D types? And there are a few problems that we have. So one is that when I have a NF4 tensor as currently implemented in torch.io, and I call to bfloat16, this actually no ops. Why does it no op? Well, the reason is very dumb. Because NF4 tensors are tensors, they have to report what their D type is. But we don't have an NF4 D type. So they report something else. What do they report? Well, the current stance we've taken based off of float8 is they should report sort of what type they're simulating. And so bfloat16 is a pretty good approximation in this case for what the NF4 tensor is simulating at a sort of at a more compressed sense. So NF4 tensor's D type is bfloat16. And when you ask for it to be converted to bfloat16, the 2 composite says, well, the D types are already the same, so I will do nothing. There's another problem, which I don't remember. But yeah, this is the one that Christian has been like harping at us on. So the question is, like, what do we do about something like this? And another broader question, which I've asked folks and which we don't know, is if we didn't have, BC constraints, how would we do this? Oh, so another thing is there's some Autograd conversion stuff involved, but I don't want to dig into that yet. So those are the 2 questions. Like, what should we do about like this problem? And in general, like, what's the best API for an NF4 tensor? All right, I'm taking proposals.
And I want to just quickly mention, I think with enough will, we can make the Autograd change.
That's also why I don't want to talk about it. Yeah, right now.
Right, so, yeah.
Driss.
Okay, so I wrote the original API, so I feel entitled to an opinion. Okay, so why is it spoofing bfloat16? NF4 is an example of weight-only quantization, and it's like you said, the activations are in some higher precision, and when you do the matmul, you dequant the weight. how was this originally implemented by me? There's two things. When I first wrote this, Torch compile did not work with subclasses, so this was not a Torch dispatch tensor subclass. And I wrote a method called get original weight, which would do the dequant. I like it. I think that works great. What can you do? You can do get original weight, and then you can call 2 on whatever you want for that thing. I think Christian is of the mindset if it like looks like a tensor and talks like a tensor, it should really act like a tensor. And I'm not convinced yet. I kind of like these weight only dequant tensors to spoof the like activation type. I think it's kind of a nice UX. You wouldn't call 2 is like the UX. You would dequantize and then call 2. But maybe that's too much burden for users and doesn't play with other systems.
NYC.
Yeah, so I guess the question for Christian or whoever is asking for the .2 to work is like, are they looking for, you know, a dequantize? Like, are they looking for that to just dispatch a dequantize? If so, why can't we just make that happen if that's the expectation? Or are they really looking for just like add a bunch more precision to it or something like that somehow, which is separate from the dequantize? And if they want that, I don't know why they want that. And I don't think, like what's the use case for making it look like a tensor and do the thing? And if there's no real use case, why don't we just dispatch to dequantize?
So Christian's not here. So Driss, I'm calling on you to answer this question, actually.
I think to the last thing that Jane said, the problem with 2 still exists. It's like you don't even get a chance to call dequantize and then 2 because of the no op. And that's what Christian doesn't like.
Yeah. I mean, isn't the first question like, what does dtype mean?
Just to answer Jane's question, like I think the 2 here is just one of the examples. But I think the root of the problem here is that some subsystem expect that looking at the dtype is going to be what is actually stored in there. And so that's why, you know, when Christian writes, I want these to now become a BF16, I want to dequantize and get a BF16 out of it. So you expect the dtype to be accurate. But at the same time, as Dries mentioned, there are cases where you actually like the fact that you're lying about your dtype. And you want, you know, these things to pretend to be the same dtype because that makes the rest of the systems we build easier to build because, you know, your NN module think all the dtypes are the same, all things like that.
But that's the question, right? It's like in the universe of use cases, some are going to like a spoof dtype and some are going to like a truthful dtype, and it can't be both. So which is it?
Yes.
Vasily?
Oh, so I guess I'm just, I don't think I have a good technical knowledge on this, but can we just have a flag on the tensor to like toggle this?
Is dtype lying?
I don't think we can because the problem is the caller is the one that expects a given semantic, not the tensor.
I guess, or is there a flag that says like is tensor subclass? And can we just like dispatch the 2 function to Torch dispatch always if that flag is true or something?
It's very simple to fix that 2 call, but that's not going to fix an NN module that assume that, you know, it is the right dtype or not.
Yeah. Or I guess, is there a way for a tensor subclass to like toggle what each of the systems do in some composable way? I'm not saying it's a good idea. I'm just trying to understand if that's possible.
My feeling is not, because they all call into the same APIs. Like, as the subclass, you see someone calling .2, assume you catch that call. Is that a subsystem that expected a valid dtype or like a truthful dtype or not?
Yeah. I guess my other question would be how much things would break if you had like a dtype which says I'm undefined or something.
I can't answer your question.
I don't know. Horace?
In the case of NF4, like, can you also just do this with a parameterization? Like, what are the downsides of doing that?
Just
You,
looking in- yeah.
what does that mean, Horace?
So you like you like I mean like basically my understanding of what we want to do with it. So NF4 tensor is like the floating point tensor. It has a scale associated with it, or
Um, there's a few tensors associated with it.
sure. But then you want to materialize it into like an FP16 tensor. So what is the point of even making this a tensor subclass?
It wasn't a tensor subclass, or it doesn't need to be a tensor subclass.
Yeah, so
or I guess
concretely,
like
when Horace proposes that it's a parameterization, what would happen is if you had a weight which was an NF4 tensor, what you would actually have is an underlying weight, which is the float or whatever. If it's an integer, that might be okay too. And then you have the parameterization, which tells you how to get from that to be float 16, and also vice versa when you're doing.
Or sorry, actually, in this case, you wouldn't even necessarily, I think, need an NF4 tensor, right? Like a subclass.
Yeah, so there's no tensor. It's literally just a parameterization for the weight.
Yeah.
Is this saying for an existing linear module, replace the weight parameter with the tensors you need, and then hook into the forward logic? Is that like another way of saying parameterization? I feel like I'm so confused in the term.
Or a parameterization is like an existing piece of infrastructure, to be clear. Like, and like what it does is that, or at least my understanding of what it does, is that basically before that parameter is used, you get to like, instead of like, when you call like dot weight, instead of just, getting the weight from an attribute, you get to call a function that creates your weight through some function. And that construction of the weight can occur by, calling, say, like dquantized on the underlying tensors that constructed.
Yeah, I think, or I guess like how does that change the
Well, there's no tensor, so we don't have to say what the dtype is anymore.
Yeah. I mean, so yeah.
Horace, I think the main difference between these two approaches is that if any other system is trying to look at the state of the module, like FSDP, like these kind of things, then they might see it in an inconsistent state, or you won't have the appropriate hooks to override what they do.
I don't understand this point. I mean, from every other subsystem's perspective, is it not just shouldn't the NF4 tensor really just look like your N4 tensor, a couple of scales on your module? Like, what is inconsistent about this?
Like when FSDP grabs the weights, it expects to be able to do things like all reduce on it.
Yeah, but I mean, if it's an NF4 tensor, you can't do all reduce on it anyways. Like, you need to support all reduce on like the. Or like, I mean, there's like a problem anyways with NF4 tensor, and I don't think we would want to do an all, like, you can't do an all reduce on NF4 tensor anyways. I mean, you could do stuff like
you could, right? You could dequantize, reduce, quantize. It may not be performant, but you can do it.
Yeah, I guess.
Right, but I think what I meant here, Horace, is that, for example, in like per parameter FSDP, we do have torch function methods that prepare for all gather, where a subclass can say, I am the parameter, but this is what you need to all gather, so that the user can overwrite what is going to be all gathered for that particular parameter. So we are using tensor subclass as extension points for other stuff than just the forward.
Is it NF4 inference only though?
No, it's like design
training. Okay.
But I don't think it does. You don't compute gradients rather than 4 tensor, right?
No.
Yeah.
Okay. I'm not saying it's a prime. I'm just mentioning that is the big difference I see between these.
Or I think maybe my like moral POV is that like I think in some sense we were discussing like what is the morally correct thing to do for something like this. And I think my opinion is that it does not have to be like a tensor subclass. I think there are like a variety of like, in some sense, I think what we really care about here is we care about taking people's existing modules and being able to transform them in a composable manner. And here, you know, the enemy and or like the thing that we're trying to prevent is essentially module swaps, which is kind of like the standard thing that people do, but that we think has issues with composability. And I think there are a variety of ways of achieving this kind of like modular application of NF4 tensors that do not have to only be tensor subclasses. And in particular, I think like parameterization is like a reasonable thing to do in many cases. Actually, to be honest, in many cases, like even if we had tensor subclasses, I feel like it might make sense to instead construct a tensor subclass out of the parameterization. I'm not actually sure what we're doing today.
NYC?
I definitely agree with you, Horace. I'm open question is the original question here of what do we do with this dtype? I feel like still stands because we have a collection of many dtypes we are working with, you know, between FP8, NF4, NF4, MX, all of that. I agree that maybe NF4 is not a valid example, but I feel like we still need to answer that question about dtypes.
Okay, but just like the ones you specifically mentioned, FP8, MX, those are different because they're special. Actually, okay, so but
Also,
FP8 is a good example. So when I have an FP8 tensor, it also advertises as being what, bfloat 16 or something. So so you have the 2 problem on FP8 tensor as well. So do we hate it? Like, is it bad? What's up?
I've never heard anybody ask for this for float 8.